like David said, I just finished my master's looking at walleye reproduction in Lake Nipissing, which is just east of Sudbury, southeast a bit. And I'm going to try and make that applicable to how walleye are going to be affected by changing environments, a little bit about my research, and then how we can kind of expect to see some of the changes and adapt with those changes. So thank you all for joining me today. Kim, I know you've probably heard most of this already because I saw you at my defense, but we'll just get into it. So walleye have naturally a large range, all the way from the far north down to southern Texas. And you can see in the yellow in this picture here that they have been introduced in the southern ranges. And some of these places aren't naturally, they don't naturally reoccur. So it's all stocked populations, but they still do naturally reproduce quite far south. So keeping this in mind shows that there is some play in the amount of temperature variability that the walleye can withstand. It also, my next couple points, you'll see that there is a good variation in health and size. So I thought something that might be interesting is seeing where some of the largest walleye have been caught. The first or the most recent was in Dryden in 2018. There was a 36-inch walleye, which was around 22 pounds. I'm gonna extrapolate on that just based on the length of the fish. And that was obviously through the ice. And then they never took it in to get it professionally weighed, so it's not in the record books, but it was measured at 36 inches. The closest fish to that was measured was in Fort Erie, which is in quite far south in Ontario. And it was measured at 36.5 inches and 22 pounds in 1943, so quite a long time ago. And then also in the States, in Tennessee there, you can see the little blue star. That was, again, like a 36-inch walleye and around 22 pounds. So these big fish pop up all over the place, and unfortunately, you don't see them as much as we did in the past in the late 1900s, so 1940 to 1980. These big walleye were quite common, and now we're starting to see fewer. But seeing that 36-inch walleye in Dryden is a good indication that they're still out there. We're just maybe the fishermen just aren't getting as good at targeting them. So looking at what makes large fish and the food webs that they rely on, walleye tend to feed on perch and bluegill, lots of small forage fish, including suckers. And if you fish for walleye, you may know that leeches work really well, as well as small cyprinids or minnows. They can also feed on deeper living fish, so fish such as cisco and the rainbow smelt are also common food for the walleye. It's interesting to note that smaller walleye tend to feed inland more, so they'll feed on perch and bluegill more. If fish such as cisco, which not necessarily are in all of those systems, are there, then as the fish get larger, they start to feed on those. So what happens is the size determination of the fish also indicates where they're feeding. But what happens is if there's no forage fish that are deeper, the larger walleye are feeding on the same food sources that the smaller walleye are. So what this means is there's just less deviation in their food sources, and this has been shown to alter some of the results that we're seeing. So what I want you to kind of take away from this is, depending on the system that the fish live in, this ultimately changes some of the dynamics you expect to see in going forward, looking at some of the other attributes. So walleye have very high recruitment variability, which means that one year they may have a very strong survival of embryos, and you'll be able to see that going forward in that year class. And other years they may have very low survival. This is thought to be somewhat due to the fact that they are selected, which means that they produce a lot of eggs, but experience high mortality or can experience high mortality. And this mortality is thought to be dependent on early life survival, as I said, on these embryos. So things such as the female and egg characteristics and the spawning conditions contribute to the survival of these embryos and the early life survival. So in their environment, walleye are quite interesting. They spawn at two different types of places, and this may be something that you're already familiar with. They spawn at shoals and shoreline sites, so this is just rocky, non-turbulent areas. And then they also can spawn at river and river plume sites. And there's evidence that they can switch year to year. There's no genetic isolation between these two different areas because they can occur in the same lake. So it's almost just where they are that time of year. But it's important to understand that walleye also, they spawn in the spring, so they have an environmental cue. So when the water is 4 degrees to 11 degrees is when they normally spawn. And this is important to know because it can change depending on the year and the environment. So things such as the water flow can change, the spring runoff in river and river plume systems, and the turbidity. So if there's a very high amount of snowfall that year, then there'll be quite a large spring runoff. It could cause high turbidity. And then also the temperature. So if it's a warm spring, the water may warm quite quickly. If it's one of those springs that it's really, really cold for a week and then really warm and very fluctuating, it may cause the water to take longer to warm up. And these things can affect the date of spawn, as walleye tend to have a set amount of temperature units that they need for their embryos to hatch. So in a given year, if the water warms quicker, the eggs will hatch quicker. And then also just the time that the walleye are spawning. If it's a cool year, the walleye may spawn later. Ultimately, looking forward, with more variable climate, you can expect to see the decreased stability and predictability of these spring warming patterns. So again, influencing or magnifying the effects of the water flow and the temperature on these walleye. Some of the previous research has shown that spring environmental conditions do have effects on year class strength or embryonic survival. It's shown that rapid warming springs, so springs where maybe the air temperature is quite warm, or the water just, there's less ice, so the water warms quicker, has contributed to stronger year classes or better survival. It's also been shown that river flow rates, when they're higher within reason, can also provide stronger survival or stronger year class strength. It's also been shown that females have an effect on the survival of their embryos. So in some populations, especially those that I had mentioned earlier that tend to feed on different groups of feeder fish. So those, the larger fish feed on whitefish and smelt versus other populations that solely feed on perch. There's been some studies showing that there's a positive relationship. So the larger females are producing embryos and causing better survival overall compared to those that are smaller. So overall, there was potential for a maternal effect. So the larger females producing better eggs to be modified by these environmental conditions. However, that was never explored. So that's what my research looked at, is how these environmental conditions affected or interacted with maternal effects on survival of the embryos. So just a little bit about my research, not too much. I used a 3-year study at Wazee Falls, which is again in Lake Nipissing. And over those 3 years, we used different warming treatments for the embryos that we collected, and looked at their survival and the time to hatch. So using this method, we were able to quantify if there was a change in survival over different temperature regimes during incubation, and if it affected the time to hatch of these embryos in these different treatments. So I'll just go quickly over a few of the key findings, and then I'll talk a little bit about how this really relates to the walleye and how we expect to see them interact with climate change and some temperature variations. So something that we found and is known, as I was talking earlier, is that there is highly variable spring spawning events. So just in the 3 years that I was doing my study, you can see here in this graph that I'll go over with you. So there's water temperature and air temperature on the y-axis. And then on the x-axis here, I use Julian day, which isn't necessarily the most familiar, but all you really need to know from that is that where that blue dashed line is, that represents April 30th in every year. So in 2017, you can see that these dots, which represent the spawning collection, so when spawning is happening, mostly occurred before April 30th. And in this system, this was considered the average spawning condition. So most of the time, you would expect to see the spawn occur before April 30th, which was, as I said, like we saw in 2017. However, when you look at 2018, if you look at that April 30th, the blue dashed line there, you can see that all 4 of these spawning dates that occurred, or the spawning events, happened after April 30th. So there's quite a large shift in the time that from one year to another that the spawn event was occurring. And then again in 2019, you can see it shifted. That blue dashed line is April 30th, started to happen more around April 30th. So in 2017, it happened earlier. In 2018, the walleye spawned later. And in 2019, seemed like it was more of a moderate year, hatching or starting to spawn beginning of April 30th and then going on a little bit more. And you can see in 2018 too, there was much more rapid warming. In 2017, you can start to see a slower warming, and same with 2019. So there is a lot of variation between year to year that just is naturally occurring, not necessarily due to climate change, just in general naturally occurring variation. And it is very dependent on environmental factors. So I'm not sure if it was the same where everyone else was in 2018, but we had very high amounts of snow that winter, which led to 2019 spring happening later. And then same in 2018, we just didn't have, just had cold weather for quite a while. So what we did is, this is our results from our water temperature study. So I'm going to go over this a little bit because some of you may not be familiar. These are bar graphs showing the embryonic survival. So looking at the means here, which are these black lines, in 2017, you can see that they're all very similar. So all around 60% embryonic survival. And what this means is that in each of our treatments, which you can see are indicated by these 3 separate bars, that there really was no effect of the treatment on survival. And this is the same in 2018 and 2019. You can see that there's very little variation in the means between treatments. So overall, what this means is there was really no negative effect of different temperature regimes. So whether it was a rapid warming spring treatment or a slow warming spring treatment, there really was no strong effect on survival. What did affect survival in some of our models was embryonic characteristics such as size, fat content, and maternal, and all of these two can be contributed to maternal investment. So how robust was the egg created? Really, if it was larger, if it had higher fat content, it tended to be better at surviving, or in these better developed eggs tended to survive better in all of the treatments. However, unlike previous research, we were able to show that there was really a weak relationship with female characteristics. So we didn't see the larger females being able to produce more robust embryos, or embryos that survived better along the treatments, which is interesting. It shows that there may be population variation, and I'll get more into that in a few slides. We also looked at temperature units to hatch, which I did mention earlier, but it's an interesting way of explaining temperature and time to hatch. Instead of using time, we use temperature units, which means we use growing degree days. Embryos don't really change much below 5 degrees. So we use every degree that the embryo experienced above 5 degrees as the growing degree day. So it's kind of a cumulative temperature quantification. And what that does is it tells us how long it takes using temperature for an egg to hatch. So in this units that we use, these temperature units, we were able to show that female characteristics such as age and size have a negative relationship with the temperature units, which means that larger females actually produced embryos and that hatched faster, so or under less temperature units. So it took them less warming for the embryos to hatch compared to those of the smaller walleye. It also showed some egg characteristics such as size and lipid did somewhat affect this, but it was mostly female characteristics that really showed an effect. And all of that to say that we were able to show that larger females produced embryos that can hatch in less temperature units. So in seasons that may be cooler, you'll start to see the larger females' embryos hatch earlier. That's what all of that means, which is interesting. And although it doesn't have a clear positive or negative effect on survival, it can contribute to survival. So I'll go into that now. So looking forward and kind of what we can take from the results that I've seen and some of the other results in walleye research is that as we start to see earlier and less predictable spring warming, we can expect to see earlier and more variable spawning times. So you may be able to say, okay, we've been starting to see our walleye spawning the end of April every year. Well, this now might start to see them shift into May. And so you can expect to start seeing these shifts of these populations. And it doesn't necessarily mean that it's going to be a negative shift. It's just something to keep in mind as we start to see these shifts in temperature changes. Now, what I was talking about with the temperature units to hatch, what this means is that with these changes in hatching time or incubation time, what you can start to see is maybe the predator and prey dynamic shift. So now some predators may be hatching earlier and are more prepared to feed on all of the eggs or the fry that are hatching, or it may mean that the predators will miss the hatching period. So maybe they'll already be beyond feeding on the embryos, and so we won't see as much predation. Overall, you can expect to see more variable recruitment due to this. So like I said, we can't necessarily quantify for every ecosystem whether or not it will be a positive or negative effect, but it's something to think about and monitor, and it will be lake specific. So if there's a few lakes that maybe provide a significant amount of biomass or food for a community, it's important to maybe monitor that lake better, just so that you can start to quantify how the shifts are affecting the population. Also, like you can start to see a removal of larger females, and this is tending to be maybe because they're caught easily in nets, or because one female or male can provide lots of food. This has been seen in many fisheries. Just more as the fishing pressure increases, you start to see a reduced amount of larger females. So going forward, this is just more of a general point. This means that there'll be higher temperature unit requirements. So that's that temperature unit to 50% hatch reference that I made earlier. And so if we only have small females in the population, it's going to take longer for those embryos to hatch. And again, that doesn't necessarily mean it's a negative thing, but we just have to consider that this is happening. So what does this mean, and how can we make this information applicable, as it's not black and white? I think there's a few things we need to understand is that there is lake to lake variability. So depending on your ecosystem, depending on the food webs that you have, it will change. So again, as I talked about earlier, with if there's perch and all of the forage fish in the shallows, but you don't have those Cisco, you can expect to see a more cohesive result of temperature change. However, if you start to see different sized females feeding in different areas of the lake on different food sources, this may make it more complex, and you might start to see some female variation and embryo variation from that. There's also lots of influencing factors, so not even necessarily in the ecosystem itself, but in the environment. So things like invasive species, any influx of pollution or increased harvesting, all of these things can cause shifts that could alter some of the results that you expect to see. There's also naturally occurring variability, again, between populations, and just in general, as I talked about, the seasonal variation in spring warming. So looking at the embryonic survival, you can already see that just from year to year, seasonally, there are differences. So the two key things that I can recommend is to do your best to maintain a healthy population. And I feel like maybe healthy is misleading, but a robust population. So try to keep a good biomass of fish in the lake as we get into these more varying times. If we start to expect to see more climate change effects, maybe damage to some of the reproductive areas in your lake, if you know that that's going to happen, then it's really important to try and reduce your exploitation of the walleye. So keeping in mind maybe harvesting, if you know that there's quite a few smaller walleye, taking a few more smaller walleye and leaving some of the older walleye, or if you've noticed it's opposite, if there's lots of large walleye, then you can maybe take a few, but ultimately just making sure you have a very balanced population and overall keeping in mind the factors that are influencing these populations. So if you notice some invasive species, maybe just giving the system a year or two to kind of stabilize and see how this is going to affect the population. If they're naturally declining after an invasive species is introduced, that's a good indication that they're struggling. So maybe give it a few more years and use a different population as a food source or fishing destination. Also, I would say the most important is providing ongoing monitoring. So you're not going to be able to tell if the populations are increasing or decreasing if you're not monitoring the system. So ultimately, if there are more important systems to your community, or that even if it's just a recreational hobby, understanding the population dynamics, is a system getting stocked, is it not? Are there invasive species? Things like these are all important to note. Unfortunately, I guess, there's not really a black and white takeaway from how walleye are going to respond to climate change, but I think it's important to understand that there's a lot of variables, and monitoring is probably the best way to understand how your specific or particular system is going to react to these changes. So really, I think that's my main few takeaways, and some of the knowledge that I can share with you about walleye. So thank you.